So let's talk about bond properties. There are only a few bond properties we actually want to look at. So we have bond length and bond strength. Now, bond length is inversely proportional to bond strength. So longer bonds are weaker bonds. So if we look at carbon-carbon single, double, triple bond, the single bond is the longest and takes the least energy to break, so it's the weakest. Then the double bond is kind of in between, and then the triple bond is the shortest. This is a typo. So as bond length increases, longer, and this holds true for fractional bond orders as well. So fractional bond orders, right? Remember, if we have resonance, we can have fractional bond orders, and we can actually calculate it. So the way you calculate it is the bond order is equal to the number of bonding pairs divided by the number of atom pairs. So for instance, if we take carbonate. Carbonate has 4 bonding pairs between carbon and oxygen, right? Our 4 bonds, 1, 2, 3, 4. And then there are 3 separate carbon-oxygen pairs, 1, 2, 3. So our bonding order is going to be the number of bonding pairs divided by the number of adding pair, or 4 over 3. So 1 1/3 bonds, which makes sense. I'm sharing a double bond across 3 different bonds, so 1 1/3 sounds about right. So that's how you calculate a fractional bond. We can also talk about, bond enthalpies. So bond enthalpies is the energy needed to break a bond. So it takes energy to break a bond, and when you form a bond, you release energy. And so we actually have tables for these, and what we can do is we can actually calculate based on this table, or these, whatever table you have access to. We can calculate what is the enthalpy for a given reaction, based on it's equal to the enthalpy of the bonds broken minus the enthalpy of the bonds formed. So the bonds broken, input energy, positive. Bonds formed, minus energy, not minus energy, but negative enthalpy because it's energy given. All right. So let's take, for instance, hydrogen gas plus chlorine gas giving me 2 HCl. So I'm breaking 1 hydrogen-hydrogen bond and 1 chlorine-chlorine bond, and I'm forming 2 hydrogen-chlorine bonds. So the delta H of the reaction, the enthalpy of the reaction, is the sum of the bonds broken from the reactants minus the sum of the bonds formed, which is the products. So it's the enthalpy of 1 hydrogen-hydrogen bond plus 1 chlorine-chlorine bond. So we just add those together. Minus 2 times the enthalpy of the hydrogen-chlorine bond. Okay? So we get 432 plus 239 minus 2 times 427, 671 minus 854 gives you negative 183 kilojoules per mole. That's it. It's pretty straightforward. So let's do some practice. First, calculate the bond order in PO4 3-. So we did this in a previous video drawing out the Lewis structure, so we're going to shortcut that. So we say, okay, I've got 1, 2, 3, 4, 5 bond pairs. Okay, and I've got 1, 2, 3, 4 atom pairs. So the bond order is going to be 5 over 4, which is equal to 1.25, or 1 1/4. Calculate the enthalpy for the following reaction using the table of bond enthalpies. Based on the provided on the previous slide. 2H2 plus O2 gives me 2H2O. So let's go back to that slide. Okay, so get rid of this ink. 2H2 plus O2 gives me 2H2O. Cool. So I need the enthalpy of my bonds formed. So 2 times HH. Where's HH? Here we go. So 2 times 436 plus O2, 495, minus 2 times, now here, remember, H2O, so I have 2 OH bonds per 1 water. So 2 waters is 4 total OH bonds. Okay, so my OH bond is 463, so minus 4 times 463. Okay, and you'll find that the answer is, drumroll please, negative 485 kilojoules per mole.